and welcome everyone to today's BMC Capacity Optimization Best Practice webinar on storage capacity management. During the last webinar in February, we asked participants to complete a short survey, and many of you did. And one of the questions we asked was, what are the major areas of interest for your capacity management process? And as you can imagine, 100% of the respondents said servers were of primary interest, but 81% of you said that storage was very important to your capacity management process. So this, is a very relevant and timely topic. As Sarah mentioned, today's session is being recorded, and it will be made available on BMC communities after the call, as are all of the prior BCO best practice webinars. We anticipate a lot of questions, and you folks always ask great questions, and we will use the Q&A window in WebEx to answer your questions. Please do not ask questions by way of the chat window. Again, we will use the Q&A window to answer your questions. Any questions that are not answered during today's session, we will answer them after the session and post them along with the recording. So you'll get to see everyone's questions and the expert panelists' answer to those questions. So it's always nice to see everyone's questions and answers. So without further ado, I will turn the presentation over to today's presenter, Mr. Sudhir Apte. Take it away, Sudhir.
Hey, thank you, Charlie. So before I begin, just a usual legal notice. All the recommendations described are the sole discretion of BMC and so on. There's no way that this content should be viewed as guarantees or warranties on BMC's part. So here's the agenda. The main part of this presentation is a background on storage systems in general, because this is an area that most people in our field are not as comfortable with as we are with the server-based capacity management. I'll cover some of the main types of storage systems that you find out there. I'll pay some special attention to block storage arrays and filers. I'll explain what they are too. And then we'll just list the storage capacity management use cases that we usually find. This section should give you a sort of orientation on how to approach capacity management for these kinds of questions. The second part, which is smaller, is about the facilities that in BCO are built in to address these issues or some of these use cases. We'll go over the BCO architecture features that are suitable for storage capacity management, the out-of-the-box connectors and farms, and on the partner integrations that we have. We have Sentry Software integration for BCO, which implements some of these out-of-the-box for several types of storage systems. So in the first part, let's talk about what do we mean by storage. When customers talk about it, they usually are talking about shared storage systems. There are various types of these. Block arrays, which are the operational storage, as we know. These are the ones they usually mean. They can also be talking about filers, which are exporting file system volumes for the OS and the applications. Then the other three types are we can talk about them as content addressable storage or archival storage. That's usually used for compliance, backup systems and recovery, and general virtualization systems, which are implemented as layers between the servers and the block arrays. So the first two items, the block arrays and the filers, the operational storage, these are the ones that are most widely used and most important, I would say, for capacity management. So we'll go into those much more detail later. The archival storage for compliance. These are used for archival of data that's not being modified anymore. So they have technology that allows you to store large amounts of data, say in the form of objects. There might be, X-ray images or MRI, things like that, which are stored in a way that allows you to retrieve them later by accessing the content, as opposed to like a file system where you have to know the name of the file. There are examples that I list, a couple of them, the IBM DR550, the EMC Centera line, and these are not usually what customers are talking about when they talk about capacity. That's because these systems are very well understood to have a fixed amount of capacity and they're sold as such. and they're used in a very specific case, which is when you have archival requirements. The backup and recovery appliances are similarly, they're used for backup of operational data and for recovery of lost data for resuming operations, obviously. Their main distinction is they are using cheaper media. It used to be tape-based mostly, now often disk-based, even though they are often called VTL, virtual tape libraries, because of the API being continued from the older days. An example of this is EMC Avamar. There are many other examples, and all of the enterprise class block arrays that are on the market also have some sort of software to enable backup and recovery. So this is often subsumed for the customer's point of view into the set of features they buy when they buy an array. But it's also possible to buy dedicated appliances of this sort. Finally, virtualization systems are there are various ways of slicing and dicing the available storage on arrays to make it easier to manage. So, for example, extract or expose some 100 or so devices from backend arrays and then slice them into smaller volumes for consuming at the server level. The actual storage in this case is provided by the block arrays or by other means. But what the virtualization system offers is an easy way to map virtual volumes to this existing storage. Examples here, IBM SPC, EMC Vplex is a newer one. There's also EMC Invista. And these are all using different layers in the fiber channel stack to construct these virtual volumes. Many of them are implemented on top of the switches, the fiber channel switches. Also, obviously, all enterprise class block arrays also offer their own storage virtualization, and this is the one that most likely you will encounter in the field. Also, on the server side, the enterprise class server operating systems also have a volume manager on board. There are also third-party volume managers, and these allow you on the server to import large volumes and break them up into smaller ones, or to combine several volumes into larger ones. And there may be several reasons to do that. Usually it all boils down to ease of management. The way that the virtualization layer has evolved so far is it usually is controlled on the server side more and more. That is, there are arrays that are usually managed by a separate group, and then there are servers that are managed by another group. And we are talking about who has control over how these volumes are configured. So the virtualization layers, because they sit between these two, could fall on either side, and they originated most of them on the storage side. But I think the most commonly used ones are on the server side now. So let's get back to the block arrays and filers, which I said are the most important for our use cases. Block arrays are special purpose computers. They are typically called names like storage processors, which expose storage space from hundreds of thousands of drives. They can be multiple racks wide, containing many drives of various types and capacities. And what these block arrays do fundamentally is to offer a block abstraction for each storage volume. So they create these things that we might call logical units, and the logical units are exposed in the form of blocks. Usually these are connected, these storage arrays, to fiber channel SAN, storage area networks. Those switches in turn are what servers plug into to access the storage. But increasingly commonly, because of fiber channel costs, it's often found that people use regular IP networks as their SAN and use a new protocol called iSCSI to connect to the servers from the storage and vice versa. And all the major block arrays that you'll find are either already offering or will soon offer iSCSI capability as well. So traditionally fiber channel, more commonly now, increasingly commonly iSCSI, and both of them are the same array. They simply have different ways of connecting to them. The key abstraction of these block arrays, as I said, is a block volume. Block volume is the same as what we might call a logical disk. A logical disk is an abstraction in SCSI. The idea is logical block addressing, or LBA, which is saying that the entire disk is visible as a large array of blocks, starting from block 0 to all the way to as many blocks as there are. And this offers a simple and convenient way for protocols and servers to access the storage. You might remember older schemes that you might have heard of based on the physical geometry of the drive. Because these were magnetic head drives, there was a CHS scheme, cylinder head sector, in which you have to specify which sector, which track, which cylinder, and exactly where the data was defined, how it was going to be accessed, and how much time it was going to be taking to access. Similarly, there was a more updated version of that called zone bit recording, or ZCAV, and that's another way of arranging the sectors on the various tracks. As you can see in that figure, one sector in the innermost circle or track might occupy 2 sectors worth of disk on the outer tracks and 4 sectors on the outermost tracks. And this all has to do with how fast the heads move and how quickly you can get to individual sectors and how much data you can pack onto these tracks. So these are all clever schemes to extract more and more capacity out of these disk drives. But all those are subsumed behind these arrays. So all that the arrays do, and even much simpler disks also, is to offer this logical block addressing scheme. And the fundamental thing, as I said, is block arrays do is to virtualize the block volume. Virtualization is everywhere in storage. So within the array, there are virtualizations. That is, the backend disks are virtualized into RAID groups and so on. I'll explain a little more about how that works until finally these volumes are exposed. Within the SAN, there may be virtualization systems like the ones I mentioned earlier. The IBM SVC is not in the switch, but it's another box that sits where the SAN sits. And IBM Invista is built directly on switches in the SAN. And on the right-hand side, virtualization is also in the OS, in the volume manager that may be on board. It may be a third-party volume manager. And there is virtualization also in the file system and in middleware. That is, for example, Oracle has this facility called ASM, which is a way of Oracle assembling together different files and presenting them to as an abstraction to Oracle, so that the Oracle administrator can talk about these at a higher level. So virtualization is good because obviously it allows you to manage them easily, all of these various devices and the storage used on them. But it also complicates traceability. That is a key complication of managing storage. And it also makes capacity management, I would say, more tedious, because in order to talk about capacity, you have to know which level of abstraction you're talking about, where is the storage you're referring to, and various tools that give you counts and capacities and so on. You really need to know where they're counting the storage. So looking deeper into a block array, here I'm trying to avoid becoming very brand specific, but overall, I think it's true to say that most of these arrays are arranged in 3 layers: the front end, middle layer, and back end. The front end is the one that's probably the most constant in the sense that it doesn't change from array to array. It is the piece that exposes the logical volumes, which you might call disk, using SCSI and fiber channel protocols or iSCSI. And these are exposed as ports to initiators or host APIs that come in from the front end. So these are the external view as far as the servers are concerned of the array. The middle layer builds virtual storage and storage pools and so on from the actual disks that are available. And this is where most of the configurable options are in the array. So the virtualization, replication, meaning the ability to create clones and snapshots and so on, backups, and all the archival features of the array, they live here. And so obviously most of the variation between different kinds of arrays is also here. Some arrays have built their own kinds of abstractions, so you need to understand what they mean by these various things. Some people call things RAID groups, some people call them aggregates. So you really need to know what the array means by these various things. The backend is also fairly standardized, I would say. It uses the actual physical drive to build the protected and resilient storage. Usually they're based on RAID. So we'll start from the backend first. This is the most familiar to people because RAID is commonly known. There are various kinds of RAID. You can see RAID 1, which is a mirroring capability. So each block is mirrored on one disk and the other. RAID 0 is a way of striping a large amount of space. So the blocks A1, A2, A3, A4, and so on are striped alternately, disk 0 and disk 1 in this example. And RAID 5 is another method of RAID that combines striping with checksums on a different disk, so that if one disk fails, you have the resilience that the overall data is not lost, and you can recreate the data, called rebuilding, so that you can get back to the highly available data state. So this is really the foundation for all the higher level of virtualization. I think it's probably fair to say that this is true for all arrays, that they're based on ultimately RAID in the back end. Different types of RAID are important to know because, of course, they affect performance and the level of protection. That's true, operationally speaking. But for capacity management, it's also important to understand that different types of RAID use different amounts of space per head. So every time you use a certain amount of resilience, you create it by using some space. So you could think of it as a tax on the disk space. We'll go into that in a little more detail later. So the backend is what usually is the tier of the storage. So when people think about, I have some tier 1 storage and tier 2 storage, they're trying to assign by convention a name to a level of service. The level of service may be in terms of I/O performance, because some configurations of RAID and backend disks are more high performing. So based on the type of drive, for example, flash drive, flash SSD drive, the solid state ones, and so on. The flash drive, you can see the numbers for all of these drives in terms of I/O performance published by the vendors. So you can tell that there are really tiers of different kinds of storage. Some kinds of storage are much more cost effective because they're very large disks and they may not be as high in terms of performance. So those will be suitable for certain tasks. And then certain ones are very fast, but they're also very expensive per gigabyte. And also based on the RAID configuration. So some kinds of RAID allow you to provide highly protected storage that may be very important for mission critical applications, whereas some other kinds may be more best effort type storage, which may be useful for QA development activities. The space tax that I was talking about, this table is just to give you an idea of how much it can vary. So we just went through the different kinds of RAID levels. RAID level 0 means simple striping, and there's no space tax because it's really saying that I'm just going to put the blocks of storage on alternate disks one by one. But of course, there's no protection either. So operationally speaking, no protection, but capacity-wise, it's very good because there's no space tax. And so on. I can go down the list. Just to give you one more example, if you look at RAID level 5 toward the bottom, block level striping with distributed parity, which means the parity bits are also distributed among multiple disks. So the space tax here would be one drive among n drives. So commonly used configuration is 6 or 7 drives for the RAID. So out of those, one drive will be used entirely for parity. So that would be the tax you would pay for having this. In other words, if you had, say, 7 terabytes of space in the back-end drive, you would expect to have only 6 terabytes of usable space on the RAID. And operationally, what this means is that you can tolerate one failure and automatic recovery from that failure. It's interesting to note that once you get one failure of a drive, then the drive goes into, or the RAID group goes into what you might call degraded mode. And in this degraded mode, it does not have any protection. So if you continue to use it, then you are operating in a mode where you don't have protection right now. What needs to happen is another disk needs to be added to the RAID group. Most of the arrays have a mode in which they can automatically sort of integrate a spare disk into the RAID group and start rebuilding. So there's a process that takes hours, and during that process, certain bits from existing disks are replicated on the new disk, and data is moved around so that you get back to the original RAID 5 configuration with full protection. But until that happens, you are in this degraded state. Moving on to the middle layer of the block arrays, here's where you get all the value-added services from the point of view of the storage system vendors for the array. So some common features are replication, as I said, snapshots and clones. These are all features that can be implemented by the storage administrator with no involvement from the server administrator, where you can take an entire disk and create a snapshot of it on a regular basis and store the snapshot on a separate space within the array so that you can later go back to it if needed. Clones is where you can take an existing disk, say a boot disk for a server, and create a clone for it, and then export that clone as a separate disk. These are all extremely fast operations from the point of view of the server admin, because they don't pay for it in terms of processing, and they don't even see where the storage is. As far as they're concerned, a new disk was magically created in the case of a clone that has all the data copied from your own disk. Disaster recovery is another major value-added service of arrays, where you can have two arrays located in different locations. And the idea is that every write that is made to one location, at least for the disks that are protected, every write is replicated to that remote array, so that at all times you have two working copies of the disk. And then there are a whole bunch of procedures that go with it that allow you to bring up a site in a different location in the case of a disaster. Data backup and recovery, as the word indicates, this works identically to third-party software that provides data backup and recovery. Compliance archiving, as I said, usually there are specific dedicated archival systems, but arrays also add this as an optional feature so that you can have compliance archiving built right into the array. The idea is that you can archive things that are being designated for archival, and then it can even automatically erase them after a certain amount of time has passed. Deduplication is an added feature for operational storage, which is that you can say, I want to turn deduplication on for a particular run or volume, and what that does is it tries to save space by noticing that certain files or large objects are duplicates of each other, and so storing only one copy. So this is relying on some backend processing done in the array in the middle of the I/O path, so that it can notice when there are duplicates. It uses hash keys built internally to notice when large amounts of data are duplicated. So every time you send a large PowerPoint to 10 people, it doesn't have to be replicated 10 times. It can look like 10 different documents, but saved in one place. And of course, if somebody were to modify their copy of the PowerPoint, then also the array notices that this is no longer a duplicate, and it creates a copy of it. So that's the deduplication feature. SIM provisioning is now very common. SIM provisioning is a way of saying that I know that these people who are asking me for all this space are not actually going to use it. So even if I don't set aside all the space they're asking for, let's pretend that I did, and let's give them disks that totally add up to more space than I have. What this implies is that every time there are writes to this disk from the server, the array has to keep track of it and make sure that there is enough space to satisfy these writes. And when the server asks for, let's say, the size of the disk, the SIM provisioning feature makes sure that the array responds correctly. This also means that you need to have some kind of alerting for when you run out of capacity, because you're likely that since you don't have enough room for everybody, that somebody's going to do an overdraw on the bank. So it's very important to have advanced monitoring and proactive alerts. So those features are usually implemented in the array along with the thin provisioning feature. Also, additional services like virus protection and so forth, which require scanning the disk and doing something specific like virus scanning, are also implemented in the array. The idea here is to offboard all this processing from the servers. There are many more that are not listed, but these are some common ones. Finally, the front end, as I said, it has two key functions. It provides protocol access to the storage, so fiber channel or SCSI or iSCSI, and it presents and maps the volumes to hosts in the fabric. That is, you have to decide as a storage administrator which host can access which volume, and so that's what we call protocol access. The array presents the fiber channel target port. So the way fiber channel works is there are target ports on the array and initiator ports on the host, and both of them need to be plugged into the fiber channel fabric. SCSI is a protocol that runs on top of fiber channel. So at the SCSI level, the array represents these targets, which are these virtual objects that contain the logical units. Logical units is the name in SCSI for disk. And each host bus adapter, that is the HBA, which is the initiator for the fiber channel, it presents fiber channel initiator ports. That is to say SCSI commands. And the SCSI level, the initiator from the host side issues SCSI commands that ultimately do the I/O. The host mapping that you're doing with the volumes are also part of the front end, so that the storage administrator can make sure that hosts are permitted access only to some volumes and not to others. The mapping is enforced by the SAN switches, because ultimately they are the ones that control which initiators get to go to which ports. So we talked so far about block arrays. Filers are slightly different. These directly expose file system volumes to servers via protocols like NFS or CIFS. So they otherwise look very similar to block arrays, and the actual storage behind them is provided by an integrated block array. That is, either it itself is a kind of array, or it has an array that's closely associated with it. And the examples are EMC Celera, EMC VNX, the unified ones that are new, and NetApp fast series. So here's an illustration of the difference between block arrays and filers. On the top left-hand side, you see a host. The host is running a server operating system and a file system code within that operating system, and I/O drivers at the lowest level. The I/O drivers are typically specific to whatever kind of I/O is being done. In this example, there are two attached disks to this host, and these attached disks have been divided into partitions. You see 3 partitions there, and there is an I/O driver that knows how to access the data on these partitions and the attached disk. So that's a common model of a host that's a standalone host. Then down below in the middle, you see the SAN-based array. Here there's an I/O driver in the host that knows how to talk SCSI over fiber channel. It knows how to connect to the SAN. And then behind the SAN is the array that has been plugged into that same SAN. You see the 3 layers within the array. The front-end layer is the one that's presenting these virtualized disks through SAN. And these I/O drivers make it appear to the host as if these virtual disks are actually very similar to the attached disks. So the host OS and everything above it, the file system as well, have no idea whether they're dealing with attached disks or whether they're dealing with array disks. Okay. So that explains how block arrays work. But now look on the right-hand side. The filer is actually looks internally very similar to a block array. But what it's doing is not only is it creating RAID groups and virtualizing them into volumes, but it's also exposing those volumes as file system volumes, which means the block storage that is suitable for hosting a set of files. the file system within the host, top left, is responsible for creating the abstraction of a file system, the hierarchical indexed abstraction that we are all familiar with, where you can take a file name and a path name and exactly find out where the data for that is stored. And the way it does that is to save an index into the partition. So each of the three partitions on the top left corner in the host are being imported by the host and used as a file system volume. So the file system code in the host is actually making sure to keep the index and all the data for a single file system within one partition. The file system on the right-hand side, the way it works over NFS, is to use the same abstraction, except that the file system volumes are the rectangles you see in the filer on the right-hand side. So as far as the host is concerned, the storage that is in the filer is not the same as the direct attached storage. It is a completely different thing. It is really file systems that are being exported as if from a different server. And they have a path name, and the path name is the one that needs to be mounted within the host file system. So they look like just like any shared drive that you might get from another server. So this is the key difference between filers and arrays. So to summarize, arrays, they plug directly into the SAN fabric and make the volumes appear as if they were attached disks to the host. So the host OS thinks that these are disks, and the file system within the host OS treats them as local disks. Whereas for a filer, they come in through the normal TCP/IP network. They look like a file system server, and they expose file system volumes via NFS. Nowadays, it's common to offer what vendors call unified storage arrays. This is a way for them to integrate both of these personalities into a single system. So these arrays offer both block and unified storage. And what I mean to say by unified here is filer-based storage. So what's unified about these storage arrays is that you can have both block and filer storage from the same array. So once you plug in or stand up the array, you have to plug it both into the SAN in order to offer block array type volumes and into the network so as to expose the NFS-based file system volume. These different kinds of storage arrays out there, however, are implemented quite differently. There's a gateway method which says, I'm a storage vendor and I'm used to creating block arrays. I have a nice array of block arrays that I've always created. But customers are asking me for file system access. So I'm just going to write a gateway that sits between my array and the network. And I'm going to just take the existing storage that I have and expose it as file system volumes using the gateway method. An example is the EMC VNX Unified. It used to be called EMC Celera. This is really very similar to what used to be called EMC Clarion, which is a block array and simply a gateway in front of it. The EMC VNX is much more tightly integrated than the old gateway used to be with the EMC Celera, but the idea is the same. And then there's a dedicated method, which is mostly used by vendors that used to offer an integrated appliance which offered filers. And the most common example of this is the NetApp FAS series. The NetApp FAS series were integrated in terms of offering file system volumes in such a way that if you looked at the previous slide, let me go back there. If you look at the bottom right of the slide, you see the filer picture. So in a NetApp FAS array, there is a RAID subsystem, and there is virtualization on top of that. And there are volumes that are created from it. But the volumes that are created using the virtualization are file system volumes in the NetApp FAS array. So there is actually no native block array support. But the way this has been implemented with NetApp FAS is by offering those same volumes as block volumes. So the unified, the transition from a filer to a unified filer, in the case of NetApp, involves adding a block level to the file system volume. So really hosting disks that are files within the file system. and then exposed through the SAN. The reason why I'm going into this is because all of this really affects how you look at the capacity of the array. The virtualization in the case of a block array that is trying to expose file system volume is different because there's one more layer. Whereas in the NetApp path file case, because the file system volumes are created first and then the files are created on top of that to offer this, offers a different way of looking at these, and so a different kind of capacity. So what are these capacity management use cases that you find often for storage? The key resources managed by storage capacity management are storage space, which is the most common one and the basic one and the one that most people are interested in. Storage I/O, which refers to performance, and the number of ports that are available, which is a scarce resource in storage. And the typical capacity-related use cases are very similar to what you find in servers, except that the resources that are being tracked are the ones above. So you want to see used versus available, which we call visibility. You want to see by client, the capacity that's been allocated and the capacity that's actually being used. And you need to see trends and forecasting. You want to see when you're going to saturate. You also want some way of arranging maybe chargeback or showback of the resources that are being used by each client. So let's look at these in a little more detail. So in the case of storage space use cases, where we said you want to see used versus available, what we call visibility. The point is you can break this down at various levels. When you say storage space, what do you really mean? Do you mean the raw space at the back end where the disks are actually attached to the array? Or at the configured level where you created RAID groups and now you're talking about the space that's available at that point after you paid the tax? Or are you talking about the host level space where volumes have been created and exposed to hosts? And if you remember, I told you about SYN provisioning. So if the array has implemented SYN provisioning, then the amount of space that you expose to hosts may be more than the amount that you've configured. So in order to talk about used versus available, you really need to know which level you're talking about of the space. That's one issue to worry about for capacity management. And there's no one-size-fits-all approach to this because each array has different abstractions and they call them different names and they expose them with different APIs. And they don't always make clear whether they're talking about raw or configured or host level. And they don't always make clear whether the metric is measuring something at the storage pool level, which may be an abstraction within the array, or at the RAID group level, which is another abstraction, and so on. So this breakdown is very important. The second one is how to count used. That is, when you say used versus available, how do you know how much is used? There is a problem that we call the touch bytes problem. The bottom line is for block arrays don't really know how much of the space that they're exposing or allocating to hosts is actually being used. Arrays are guessing based on the IOs that come in. So every time a server writes a byte, then the array assumes that that byte is being used. And if the array never sees an IO coming in from a host for a particular byte, it assumes that that byte is not being used. Which is all very well, but the problem is that sometimes operating systems like to, on boot up, write all over the disk. Maybe they want to zero out the disk or something like that. Sometimes applications do the same thing. When they are using raw disk directly, then they can come up and the first thing they do is to write all over the disk. So that's one problem of the touch byte. In which case the array will not know really very well how much of the disk is actually being used. The second reason why the array doesn't know is because the file systems on the OSs that are running, they don't really delete the bytes that they use automatically. So for example, you create a file, a large file, so that counts as written bytes. So the array says, okay, these bytes are used. Then at some future time, the file system deletes the file. But it doesn't actually erase any of the bytes on the disk, first of all. And secondly, even if it did, the array would not know that it's deleting a file. It would just see IOs at that byte level. So the end effect is that from the array's point of view, it creates this huge disk and offers it to the host. And over time, it keeps seeing IOs to all the different bytes within that disk. So eventually, the entire logical disk gets written, and that's all it can say. The array can never know really how much of these bytes are being used. So the numbers that are coming from these arrays need to be taken with a grain of salt. It's not always the case that just because the array says the whole disk is being used, that it's actually being used. The second kind of storage space use case is I want to see by client capacity allocated and used. We already talked about what used means, but there's another more basic problem here, which is the mapping to the host is often not automated, meaning to say that if I take a whole bunch of logical disks and if I expose them to many, many hosts, then how do I find out from the array which disks are being exposed to which host? This is not something that's standardized. So you can write an API to extract data from this kind of array, but not you still have to write new code when it comes to another array. Also, mapping to the host may involve many layers of virtualization. So as I said, within storage, there's many levels of virtualization. I didn't even mention that there's also the hypervisors. So as we all know, it's very popular on the server side to create hypervisors that ultimately run the operating systems as guests. So in that case, you need to go through that layer of virtualization as well before you can find out who is actually using the space. So when you're talking about mapping to hosts, let's take the example of VMware. If a VMware guest is directly mapped to a disk drive on an array, then you have what you call RDM in VMware terminology, which is I think that means remotely mounted disk. So RDM is a way for the VM to directly map the disk, but most often that is not how VMs use disk space, right? Usually they simply create a virtual disk on a data store. So in that case, you don't really know which of these VMs is using a particular disk unless you go through the VMware API and do the mapping that way. So the information we're looking for is storage mapping, but the information itself is not available from the storage in this case. So all that the storage array will tell you is that it is looking at a particular mapping for a disk that is going to a particular ESX host. But then you have to also map that further to the guest, the VM that is running on that ESX host. So this is a major problem. And until you stitch this together, you cannot see by client capacity allocated and used. You need to either use some kind of convention, which your tool can learn, or you need to have tools that can go deep into these particular APIs and extract these mappings. The next kind of use case is trends and forecasting saturation. This is, of course, straightforward with the BCO features once the data is available. This statement, of course, can be made for the previous two use cases as well. So use versus available is straightforward to handle in BCO. Client capacity by client allocated and used is easy to handle with BCO features. The hard part is getting the data. The same argument goes for the last use case, the chargeback and showback use case. This is also straightforward BCO features once the data is available. So here's an illustration of the storage space levels within block arrays. The host level, when you say how much capacity is allocated, you would look at these things in the sense of a thin pool has so much space available to expose to hosts. So thin pool A and thin pool B, which has this much nominal space that they could allocate. But in fact, it is based on a smaller amount of space on the RAID 1 and the configured level. That's the space that's actually used to create volumes when somebody creates volumes. So if you add up LUN1 and LUN2 at the top, they might together be even more than what's available in RAID 1 alone. On the right-hand side of this diagram, where you see RAID 2 and simple pool and LUN3, that's a more traditional way of looking at the data without SYN provisioning, where you can see that the simple pool, you might find that the space in the simple pool is equal to the space in the RAID group, and LUN3 plus LUN4 is no more than the space available in the simple pool. Here also notice that there are LUNs like LUN4 which may be created by the storage administrator only for internal use, for example, as clones or snapshot backing stores. So in that case, what the array reports as number of LUNs and the amount of space in the LUNs may include LUN3 and LUN4, whereas in fact you are interested only in what's available by exposing to host, which is LUN3. And at the raw level of the backend, you can see that these are the actual disks that are in the array, so their nominal size will be probably quite large. But some of them, like BE0, are reserved for storage processor operating system use, and some like BE5 are reserved for hot spares, which are needed only when you're rebuilding a RAID group. So the actual backend space you have is only BE1 plus 2 plus 3 plus 4, and those are being used to create these RAID groups. So this illustration is only to show you that there are many gotchas when you try to interpret the space numbers that you get from arrays. And you need to really know a little bit more about how the array is structured in order to extract the right numbers. We so far looked at storage space, but there are also I/O use cases. These I would consider a little bit more advanced because I/O is notoriously difficult to track down, especially with these many levels of virtualization. But what people want to see is used versus available in visibility, just like you do for space. But you want to see breakdown at various levels. At the HBA level, the host bus access level, the switch level, and the array front-end port level. How to count how much available capacity is there? That's very similar to how you count how much network capacity is available. It's not automated at all. And you need to know a little more in order to decide how much I/O capacity you want to allow. There are also complications introduced by the hypervisor I/O control features. So in the case of VMware, in 5.0, they released a feature called storage I/O control, SIOC. And what that does is it prevents any one virtual machine from hogging I/O bandwidth. So they throttle the bandwidth. So there's the hypervisor level. There's a monitoring process that continuously sees how many I/Os are being output by each VM. And when it exceeds certain thresholds, it throttles it back. I mean, I'm simplifying. What it's really monitoring is the latency that you see. And based on the latency, it figures that the I/O has gone beyond what the backend can support, and so it throttles the I/O. So with these kinds of features, you don't really know how much I/O capacity you have. So you need to take a slightly different approach in how you approach this use versus available issue for I/O. There's also by client capacity allocated and capacity used, which is desired. Here again, some of the same issues come up. How to count allocated, because I/O capacity metric is not automated, as I said before. And the mapping problem is again manifest here as well. So you don't know which hosts are being mapped where. For the trends and forecasting saturation and for chargeback and throwback, again, these are one level above two use cases. So once you have the data, then the BCO features are fairly straightforward to use. We said that there was a third resource that is scarce, which is the array ports. This is a much more storage-specific use case. The point is that the front-end ports for fiber channel block arrays tend to become bottlenecks because all I/O goes through these, and the arrays themselves are licensed based on the number of ports as a result of that. So the number of ports becomes a doubly important resource. One is the fact that you paid for all these ports, and secondly, the fact that the ports really are limiting your I/O capacity. Because you put switches in front of the array, the SAN switches, they enable fan out of the fabric, but still the resources ultimately are typically limited at the front-end ports, because in terms of memory in the storage processors as well as the I/O capacity, the speed of the front-end ports is also limited. So there's some rules of thumb you can have that say how many HBAs you can connect meaning how many host bus adapters, that is to say how many hosts ultimately, are connected per FE port, because these share the communication capacity and connections. And then there are also guidelines in terms of IOPS, the IOs per second, which also depend on the configuration. So the one that makes sense here mostly is capacity visibility as far as the use cases go. So how does one determine the capacity of each port? That is also unfortunately specific to the configuration. So the things that drive the capacity of a front-end port are the raw speed of the front-end port as well as the capacity of the overall storage processor. So far we've looked at the overall storage area and what kinds of use cases make sense for capacity management. Now we'll see what facilities in BCO are mostly useful for managing storage capacity, the BCO architecture features, the out-of-the-box connectors and farms in BCO, and the partner integration that we have for BCO. So for storage, we can look at the architecture in this way. It's very similar to how we look at it for servers, which is at the bottom from the storage environment, you have connectors. You have out-of-the-box connectors, as you know probably, for some of the EMC block arrays for NetApp filers. And for other data sources, you can write custom connectors. Plus, on the left-hand side, you see Sentry connectors for some arrays. And then the rest of it is the same as usual for BCO. The analytical modeling and reporting engine at the top with some out-of-the-box and custom dashboards. Plus, you can do analysis, forecast, and extrapolations and so on. So the BCO connectors for storage, in the list of connectors, you see two that are highlighted on the left-hand side, the EMC storage scope control center connector. Control center and storage scope is the component, the software component from EMC that allows you to manage multiple arrays. And the out-of-the-box connector that BCO has is capable of recognizing data from this storage scope database and extracting it. This data deals with Clarion and symmetric arrays. Similarly, the NetApp Data Fabric Manager connector is based on the Data Fabric Manager software from NetApp that allows you to manage multiple NetApp filers. And this connector connects directly to the Data Fabric Manager through an API and extracts data. On the right-hand side, you see the partner integration. We have Sentry Software integration to BCO, which uses SMIS connector to connect directly to EMC arrays and to the Hitachi Device Manager software to extract data about multiple Hitachi storage systems. Capacity visibility, there are some built-in storage farms that allow you to look at the usual kinds of views that you're used to from, say, virtual farms and so on, which tell you used, available, and so forth. Also, days to saturation. You can do analysis in the workspace from BCO. So you can analyze the utilization. You can find the busiest periods and any periodic behavior. You can identify optimization opportunities, in other words. Time forecasting models for predicting future utilization and saturation date. You can also have it automatically notify you using an alert. And you can also identify how potential changes could postpone or eliminate the saturation. So there are, you can build extrapolation models too. You can correlate resource utilization and business drivers. So number of users versus disk space, for example. Identify spare capacity and predict saturation. So you can do it also in terms of business drivers. And the accounting and chargeback analysis, you can create fixed and allocation and utilization-based cost models as usual. You can define a target hierarchy and resource allocation, again, assuming you have the mapping that we were talking about before. And you can automatically generate accounting and charge or showback reports. This shows more time forecasting using BCO storage data that's imported into BCO. The allocated space goes up and you can use that automatically. You can also do what-if events You at a certain point add space and see how much time that buys you. And finally, a word about the new Sentry Software integration we have for BCO. They have supported connectors to EMC via the SMIS provider. SMIS is a standard for the storage management interface, and many vendors have SMIS APIs exposed, and one of them is for EMC. EMC provides a common SMIS layer, a software layer that you can install on a server, and using that layer, the Sentry connector will connect to individual EMC arrays and extract the data. It also has a supported connector to Hitachi, as I said, via the device manager software, which has its own database. These populate out-of-the-box BCO view that already exists, the EMC storage farm, starting with BCO 9 or SP1. The supported platforms are the EMC symmetric DMX, the various DMX numbers that you see, the symmetric VMAX series, and the EMC CX4, CX3, these are carry-on, and the new VNX series. Hitachi, they have these platforms that are listed here. Note also VSP, the last one that is really more of a virtualization block array. The way it works, again, the EMC SMIS agent needs to be on a server. In the center, you see that. And the ETL or the connector on the left-hand side communicates with this SMIS agent on this server, which then communicates using EMC's proprietary protocol with the EMC arrays. Similarly, for Hitachi, the Hitachi device manager is used to extract data about multiple arrays. That's pretty much it. For all the out-of-the-box features that I showed you, there are references here in the slide. Most of these references are integrated with the BCO online documentation. The Sentry software integrations are described directly on the Sentry site. So that's pretty much it. Charlie, thanks. Back to you.
Thank you very much, Sudhir. Thanks for the background on storage systems and for a great overview of BCO's storage capabilities. I'm looking at the questions, and I can see that a lot of questions. It's hard to provide real detailed answers in the Q&A window. So what we will do, as with all of the BCO webinars, we look at the questions, we add more to the answers, and then post the answers to the communities page as the recording as well. This particular session on BCO for storage wraps up, concludes our series. This is the second series of BCO webinars. There were 5 webinars, 5 different topics in this particular series. So I urge you to go back and listen to the recording. These have been very popular, and we're looking at continuing the series, and we will provide information as the specifics come available. Until then, you will get an email letting you know in the next couple of days when this recording and Q&A is available. Thank you again, Sudhir. Thank you for the panelists behind the scenes that are answering all the questions, and thanks to everyone for attending this webinar. If you want to immediately learn more, please contact your BMC salesperson and look out for the email, which will let you know that the recording and the Q&A are posted to BMC community. So then, thank you very much, and have a great rest of your day, folks.